I'm going to talk about a derived class instance top-down and derived TTG. Okay. Oops. What happened? In programming language like Java, you use a package called Lombok so that the user can write some annotations to generate two-string functions and equal and hash code functions automatically. And in Rust compiler, they introduce this derive attribute to implement traits automatically. Traits are some concept like Haskell class. So you write derive partial equal or clone trait, then it will generate the code for you. And in Haskell, we have multiple deriving mechanisms in GHC. Like we have built-in deriving mechanisms for common classes like show and equal and order. And we have generalized new type deriving to derive a, this should be new type. So for a data type with one constructor and one field, we use this new type deriving stuff. And also we have generic programming techniques and derive any class. So if you want to serialize this data type T, then you can derive generic type class and then binary instance here. Then you will get encode and decode function that can be applied to TA, right? Also, template Haskell-based approaches like ASIN library. You use some meta-programming function, derive JSON, and to make from JSON to JSON functions generated from this code. Also, we have deriving via an instance via a model template by using this language extension. Also, we have many more language extensions in order to derive class instance automatically. So there are basically about 12 out of 130 language extensions related to instance deriving in GHC 9.10. So it's about 10%. I know the slogan is being lazy with class, but recently I understand in this way by not writing class instance code as possible. When I was writing Haskell code, I encountered a problem. Current deriving mechanism focuses on only one instance and one class deriving. Then if you have composite data types, like 100, let's say, like it's an AST, the data types are composited together as a whole. And each of which is a deriving clause. Sometimes it can be a pain to write those deriving stuff, right? And also we have one class may have multiple superclasses. Like I'll give you an example later. So when I handle this problem, I just write a standalone deriving from the top level type and see the errors emitted by GHC and do some interactive programming. This is not a good experience. Possible cases may be in Haskell AST in this package. There are about 78 data types. Imagine you need binary instances to serialize the AST into your disk or send over the internet and want to encode the AST with JSON by using some template Haskell techniques in ASIN package. Then you need to write a lot of trivial code. For superclasses, imagine you have this data type, like a wrap with this double with a constructor. And you want to make an instance of real float. And there will be many superclasses. And I can't remember them all, and I still need to interact with the GHCI. My early solution is like this. I use macro to write down the data types. However, there's a problem with that. If the data types are from a third-party library, then you can't, force the third-party library to write the code like this, right? And you can't change the third-party library, actually. So pretty bad, actually. The idea is that we can just traverse the data type declarations and generate the instance declarations with Template Haskell. We provide 4 kinds of APIs. First is to generate empty instances declaration for the default instance provided by some generic programming techniques. Even though we have derived any class today, I still provide this API. And we can generate standalone deriving declarations of types by using built-in mechanism of GHC. Also, you can use some template Haskell techniques to traverse the data declarations and apply the template Haskell function to generate all the class instances. And generate a class and a superclass instances for one type. So I provide these 4 kinds of API. I'll let's see the 4 kinds of API. For instance, it's just you provide a class name and a type name. I will give you the declarations. And here, the functions with this with, end with word, you can give some parameters to specify, to do some customization. I will talk about this list and this context generator in later slides. Because as you can see here, we need context generators, but in template Haskell, we don't. And for deriving superclasses, you just need to give class name and type name. It will generate the instances for you. So my sketched algorithm is that for a given type T, we need to generate an instance of class C. First, we check if T is an instance of C, or the instance of T is generated by our algorithm. Then we do nothing. Otherwise, we infer the T's class instance context and generate the instance declaration. And for each type constructor in this type T, we kind of traverse the types, and we apply this process recursively to generate the data declarations. The bold part here and here highlight 2 issues we need to solve. One is the instance function in template Haskell library. It doesn't work with polymorphic types. We have to solve this. Second, we need ways to infer the context in the standalone deriving declarations. So for the first problem, is instance is not working on polymorphic types. So if you put this kind of code, say for all equal A and a list of A, you ask whether this is an instance of equal, the function will return false. It is not in current GHC implementation. But Ryan Scott suggests that we can use any instead of this polymorphic parameter to pass it into this as instance function. It will return true. So this is kind of a trick to solve this problem. Then I use SYB library to substitute all the polymorphic type variables with any type before applying its instance function. Then this problem is solved. Problem 2, we have to infer the context. But normally, we do not need to write the instance context here or here, right? However, for standalone instance deriving, you have to write some context here, right? We have to, field or inferred, since we have to use standalone deriving. But for APIs with template Haskell, the callback function will infer the instance context. So that's the reason why we do not have the context generator parameter with this template Haskell API. So how can we solve this problem? Ryan and R.W. Barton noticed that we can just leave the type, leave the context as a whole there with viewed card here. But we need to enable a lot of language extensions, and the GHC will infer the context here. So in this case, GHC will emit warnings. And my question is that okay to just remove those warnings by default? Because normally I do not care about the type which is filled by the compiler here. The second solution is we just put all the field types into the context. Like if we derive show instance for list of A, this new data type, we put all the fields, this field and this field, into the context and give the to put a show list here, right? So we put all the fields into the context. Then for the HS module, it will be this, and module name and special con or q, then put a q name here. These are all the fields of q name. So we put all the fields into that. Then we can solve the problem, right? However, I want to infer the context a bit. So I introduced a structure. It seems to be very complex, but I will give you a concrete example later. So in my data structure, I use I. It is a set to store inferring types. I use P. It is a map from type names to the type parameters. This can be initialized before the generation process. And F is actually some context field types. During the inference process, I will substitute these fields interactively with traversing the data types I need to infer. I will give you an example later. S is a substitution type which keeps tracking of the substitution field in a data type. And R is actually the result store inferred data context to avoid duplicated inference. I will give you a concrete example. My concrete example is here. There is a P and there is E and there is a proxy-like type. And this P has only one field here. So I is inferring the type we are inferring. So P is the type we are inferring here. And the P is the parameter of the type. We can initialize by this one, right? By P, there are two type parameters. And for E, we have X, Y as type parameters. For PX, we have Z as the type parameters. And we put the fields into this F. The goal is to eliminate kind of this E and to see, look into this type and this type. And we construct a substitution And this substitution is constructed from P because in this E for this type A is from X. For this PXB is from this Y. So we construct this kind of substitution here. And next, we can't do anything because we haven't inferred E. We put E into this I. And we put all the fields of E, which is this X and this Y, into this F. And the E only has only type variables. So the inference terminates here for E. So we will put it into the result here. And now what do we do? We can substitute. We already know the fields, context field of E. Then we can somehow substitute this fields of E with this substitution. And in this way, we eliminate E in this F for P. So we have A and PXB here. And next, what do? We infer PX, the context fields of PX. And the PX, we do not need anything because there's the type parameter is phantom. We do not need anything here. And when we do the substitution for this PXB, then it vanishes. So we eliminate this PX. For the fields of P, we need only A. So we eliminate the phantom type parameters. We only keep only the necessary data type in the result. So, however, the implementation has bugs, and it cannot handle mutual recursive types very well. I still need some work. And currently, it doesn't work with Haskell source ext. But it seems to work fine with ST types in Haskell SRC and the GCST types. So, next, we need to talk about the generation control. Normally, types like integers, like some other types, we don't deriving a class for them normally, right? Imagine you have a class called a number of data constructor, and that can return the number of data constructors of an algebraic data type. This class needs no instance context, and the generation process might need to stop on integer, right? Here is my class, right? And for this integer, we have to stop the generation. Then you can put it into this list. Then the generation will stop on the integer type. You need to some sort of control of the generation. And another example is non-exported data constructors. You can't look into a constructor that is not exported, like a ratio. When you have this type, right? You want to derive like generic. Then this data type, the constructor of this one is not exported. So the generation has to stop on ratio. You have to control it. And superclasses, it's very easy. You just write deriving superclasses and real fract, and you will get all the superclasses here, right? But for mutual recursive types, you have to write them together because there's a staging problem, okay? And here I suggested to use derivings to specify the two types together. Okay. So the future works of derive top-down. Maybe I'll give an API function to derive all the dimensions, the superclasses and the types, and infer the context correctly, and add a language extension maybe called type family context. I'm not sure this is a good idea to put a type family put type family into the instance context by the compiler. Maybe I should implement this as a plugin. And maybe during the implementation, I find I have to import a lot of data types. Maybe import top-down is a good idea. I'm not sure. And next I want to talk about TDG generation. The TDG generation is...
I think you may want to wrap up soon.
Okay, yeah, 2 minutes. Okay.
1 minute.
Okay. The TDG is, you can just derive TDG automatically, and you just specify the types. It will generate the type families and the extensions for you. And you can do some simple decorator and specify the type equations, what is on the left type and what is the right type and the default type. It will give you this type family declarations. And if you want to more control with the decorator, like here, you have to pass into a callback with the argument as this type variable of the type families. So it's in this way you can generate some the TDG automatically. And in the future, I may consider to generate pattern synonyms for the TDGs. And this is the project URL. And I want to thanks to Ryan Scott and Richard Eisenberg for discussing the issues with me. Okay, finished.
Questions? Yes.
Hi, nice work. You mentioned there were some compiler warnings that came out when you used an underscore, not gave something a name. And that reminds me that this shows up in code generation, in metaprogramming quite a lot, where something deserves to be a warning if it's written by the user, but it doesn't really deserve to be a warning if it's written by a code generator. Do you agree with that? Do you think that's the case here, that these are probably not worth a warning because they were automatically generated?
I think even this is not generated by the compiler. It is written by the users. We shouldn't give any warnings because I just don't care what the type is normally.
Oh, I see. So for everyone, even for human users, this shouldn't have a warning. Thank you.
Maybe let's take one final question when the next video.
But I mean, if that's so, you can just turn off the warning. Like if you, I thought that the whole issue here is that you don't want to turn off the warning because if the human writes a type that uses partial type signatures, you still want to have the warning.
Yeah.
So I think you're right. Yeah.
Yeah.
All right. Let's thank the speaker again.